seminar of geometry and, well, mathematical physics of the University of Lisbon. And today we have again Professor Sean Lawton from George Mason University, and he'll talk about Poisson maps between character varieties.
Right, well, thank you, Carlos. So this is the second talk of two talks I'm giving here, and the first one was a week ago. So I already then said, thanked everybody for the invitation and for being here and how much I love Lisbon. So I'm just repeating that because it's still true. Okay, so I'm gonna, two things I learned last time was when I have a mask on and I'm giving a talk, I should have the microphone more sensitive or maybe even talk like this to make it better. And the other thing is my laser pointer doesn't show up on the YouTube live. So I'm going to be using this bamboo stick here. So I'm going to be, so yeah, this is the title of the talk, Poisson maps between character varieties. And let's see. And this talk is about a paper that is reflects collaborative work with Indranil Biswas, Jacques Hurtubise, and Lisa Jeffrey, and here's the arXiv posting of the paper if you would like to read all about it. I'm not going to talk about all the things in this paper. I'm going to focus in on aspects of this paper that I know best, and in particular, I'm going to discuss the parts of the paper that extend prior work of mine from 2009, or at least it was earlier than 2009. Actually, a lot of it was from my PhD thesis in 2006, but the work was published, and this is an extended paper from my thesis, and then this is sort of a follow-up paper. But this work really is, in turn, based on work of my doctoral advisor, Bill Goldman, the symplectic nature of fundamental groups of surfaces and invariant functions on Lie groups and Hamiltonian flows of surface group representations. These are both two famous papers at this point. In addition to what I'm going to discuss, which is sort of building off these papers, in this paper, what I'm not going to discuss is a sort of different way to look at character varieties than I'm going to. So I'm going to think of character varieties as moduli spaces of representations of surface groups, okay, for both closed surfaces and surfaces with boundary, which I'll sort of take some liberties and just refer to as open surfaces, even though they're not open, they have boundary, but in any event, they're sort of, I don't know, I think of it as one of two cases, open and closed. If we remove the boundary component, they actually are open, and topologically, they deformation attract to the same one complex. So if you care about topology of those surfaces, there's not really much difference. Okay, so another way to think of these moduli spaces, instead of thinking of them as moduli spaces of homomorphisms or representations, is to think of them as moduli spaces of flat connections on bundles. Okay, and what I'm not going to talk about in the paper is the fact that we discuss Poisson structures and in character varieties and Poisson maps between character varieties understood through that lens. So understood through the lens of the moduli space of flat connections. Okay, so if you're interested in that, I will encourage you to look at the paper because there's all kinds of interesting and good stuff there. Okay. Okay, so here's an outline of what I will discuss today. Okay, I'll tell you about character varieties, again, from the point of view of what's called the Betti moduli space, or the moduli space of representations. And then I'm going to tell you about the Poisson structure in those terms. Okay, and then we're going to talk about mappings between surfaces and how they, and these are topological mappings between surfaces, and how they induce Poisson mappings on the character varieties. Okay, that we're going to discuss. Again, thinking about these spaces as moduli spaces of flat connections, one of the differences, you should assume the surfaces in that case are smooth and your mappings between surfaces are smooth, okay, and you want to get rid of the boundary components so you have honest manifolds, okay. But the part I'm going to talk about is really the topological aspect where you don't need to assume anything, you don't need to assume anything about the smooth smoothness of any of the maps or spaces. You just simply think about the topological surfaces and the sort of algebraic structure of the moduli space. Okay, all right, enough fine print. Let's get started. So I'm going to begin telling you about reductive groups and the aspects of reductive groups that I think are important for this discussion. So I'm using the laser pointer again. I keep forgetting that I'm not supposed to be doing that. Okay, anyway, so we're going to let G be a reductive, a connected reductive affine algebraic group over C. And so one can always look at the derived subgroup, which sort of is the maximal, like, semi-simple subgroup of G. There's something called the central isogeny theorem, which says that G is isomorphic as its derived subgroup quotient with a maximal central torus, which is just a product of C stars, quotiented out by some finite central subgroup, which arises as the intersection of the derived subgroup with this central torus. Okay? So this is a theorem that every connected, complex reductive group, has this structure. And if you want the general, a quick and dirty definition of what this class of groups is, you can think of them as being, all of them have a maximal compact subgroup, and such groups are real algebraic subgroups. That's a theorem, not obvious, but if you could always look at the complex zeros of the defining real polynomials of your maximal compact, and the result will be some complex group, and that complex group will be reductive, and any definition over the complex numbers you come up with for a complex reductive will be equivalent to that. Okay? All right. All right, so that's a definition and a theorem here. Okay, so G acts on itself by conjugation, and so I'll just denote this by G mod G is the GIT quotient of the conjugation action. I'm not thinking of the left action here. You might think that notation suggests that, in which case this would just be a point. That is not what I'm saying. I'm saying G mod itself by conjugation. Okay, and we're taking the GIT quotient, geometric invariant theory quotient, which loosely is just, we just look at the conjugation orbits that are closed. Okay, closed conjugation orbits. Okay, now a general theorem says that that's actually isomorphic to the maximal torus. That's not this maximal central torus, but the actual maximal torus in G, mod the Weil group. You can get rid of the double mod if you want, because it's a finite group acting, so it's just the W orbits, okay, of points in the, with the Weil group acting on the torus. Okay, and so there's a theorem. And so by potentially enlarging F in this picture here, we can assume DG, the derived subgroup, is simply connected. Gotta try to get back to this. I wonder if I can, yeah, okay. Yeah, I'll use two hands. Okay, we can assume DG is simply connected because you can look at this universal cover, okay, and then that you're introducing some additional finite group action, quotienting by the some finite group in the center, right, of the universal cover, okay, which is necessary, still semi-simple, and so it's going to be a finite central subgroup up there. Okay, so anyway, by enlarging F potentially to assume DG is simply connected, we can use results of Steinberg to show that this quotient here is actually isomorphic to an affine space where R is the rank of DG with a Cartesian product of this maximal central torus quotiented out by a finite central subgroup. I mean, and F now is not necessarily the same F. Okay, it's potentially enlarged, so DG is simply connected. So when I say it's a finite central subgroup, I'm really thinking of it in the universal cover of DG. Okay, all right, so it's finite and central there. Okay, and in any event, you get this nice picture here. Okay, all right. So we're gonna care about points here, and so I'm going to use this notation here to describe points in this GIT quotient. Okay, so the tau's will correspond to these are going to be like invariant functions on the DG, okay, and these are coordinates of the maximal central torus. Okay, so I don't think I gave an example in the slides, but I mean the example you should think of is like GLN. Okay, so for GLN, the tau's are the coefficients of the characteristic polynomial. Okay, except for the determinant, and that's what the deltas are. Okay, so you should think of the taus as the coefficients of the characteristic polynomial for the derived subgroup of GL, which is SL. Okay, and so that's, you know, and then the delta will be just a determinant. Okay, all right, and in that case, the maximal central torus is just, right, the scalar matrices, right, and so that's that. Okay, and that parameterizes C star. All right, very good. But this picture is more general, as I just described. All right, so the next ingredient here is surface groups. So we have a topological surface that's compact, connected, orientable, and you know, has some genus. We're not assuming it's 2 or more. We're assuming just, you know, any genus. We also include the closed case, so we might not have, you know, any boundary. But if we do, it's a surface with boundary. So it's a finite disjoint collection of circles. Okay. Okay. All right. And then we are going to make some assumptions on n and g. We're going to assume that n is greater than or equal to 2 if the genus is 0, right? Since otherwise the surface is simply connected, and the moduli spaces we're going to consider in those cases will therefore be 0. I mean, it will be a point. Okay, because right, if you take out if you have genus 0 and you take out you have no boundary components, it's a sphere. Okay, fundamental group's trivial. If you take out have one boundary, the complement's a disk. Okay, and it contracts to a point. Either way, there's no moduli space. Okay. Okay, so since we're going to be talking, the moduli space will be in terms of the fundamental group of the surface. All right. Okay, so here's a presentation that we'll use for the fundamental group of our surface. You have, you know, 2G generators for your usual closed surface, and then you have you've taken out n open disks, okay, and so you get n boundary components, okay, and then if you have like the usual two G-gon, right, way to describe the surface, you have, you know, n circles or holes, right. And going once around the boundary of that 2G-gon is equivalent to going around the product of circles, boundary circles. Okay, and so you get this relation. Okay, and G acts by conjugation on the set of homomorphisms of the fundamental group of this surface. It doesn't. In this case, the surface is connected, so we just have some base point. Doesn't really matter which one we pick. And for now, it doesn't matter. And this thing naturally lives inside G to the 2 little g plus n, G to that power, or the Cartesian product, okay, of that many copies, okay, because you have that many, so representation is determined by evaluation, by where it sends the generators of the fundamental group, okay, and then you have one relation, so that gives you a condition on this tuple, okay, so it's not the whole thing, it's just, right, it's a subset of that. Okay, by this evaluation map. Okay, all right, and so maybe I'll point out if n is greater than 0, though, this is just a free group of rank 2G plus n minus 1. Okay, and so then this would be identified with could be identified with just, you know, 2G G to the 2G plus n minus 1 living inside here, and otherwise if n is 0, then it's, you know, it's not it's a proper subvariety of this product of Lie groups. Okay, all right. So what is the character variety then? Well, G acts on this by conjugation, and so this is an affine algebraic set, and this is a reductive group, and so the GIT quotient makes sense, and so you just take the GIT quotient of this set here, of this algebraic variety by this reductive group. And so if you want to, you know, have a description of this, of the complex points of this, you could think of this as parameterizing the homomorphisms whose conjugation orbit is closed. Okay, so, you know, I think from a GIT point of view, you should maybe think of it more like you're identifying orbits whose closures intersect. Okay, but within every such extended orbit equivalence class, there is a unique closed suborbit, and so you could parameterize it by the closed orbits if you'd like as well. Okay, all right. Anyway, so that should give you some sense of what this thing, at least what the points in here parameterized. Okay, so here's a lemma. So this lemma really isn't new. You can find every facet of it in some paper somewhere under some conditions. I've never actually seen it written down in a way that it handles every possible case in a uniform formula. Okay, so I thought it'd be fun to write it down. I'm not going to prove this, but anyway, so when G is non-abelian, and on the next slide I tell you what happens when G is abelian. It's rather trivial. Anyway, but when G is non-abelian, the complex dimension is in terms of the Euler character, not the negative Euler characteristic of your surface times the dimension of G plus some correction factor. Okay, and the correction factor pretty much depends on, there's 4 cases. Basically, it breaks down in like this. You either have a closed surface or an open surface. Again, I'm using open loosely here, but not closed is what I mean. You either have the closed surface or the open surface, and in each case, there is one special case where the fundamental group is abelian. Okay, and if it's abelian, that's a separate case because the isotropy of the conjugation action will be higher. Okay, so basically that's how that goes. So I'm not going to prove this, but loosely speaking, in every single case, what do? You have a quotient of the homomorphisms by G, so what do? You count the contributions to dimension to the Hom space, and then you subtract off the equivalent, the dimension coming from the equivalence relation, and then in some cases you have to subtract a little bit more because you have some additional isotropy. Okay, so let me just write down. Let me just show you one case of this. The first case that's here. Okay, so the first case here is when you have boundary components and you have this case here. This just means so we already said when you have at least one boundary, the fundamental group is a free group, and this condition is equivalent to saying that free group is of rank 2 or more. Okay, so in particular, it's not abelian. Okay, all right, and so that's maybe the easiest case here. And I also should point out this notation S and R are from the earlier slide, from the description of reductive groups. So R is the rank of the derived subgroup, and S is the dimension of the maximal central torus. Okay, all right. So let me just right, R in this case, right, is, well, you have 2G. Maybe I shouldn't use R here. Yeah, sorry. Let me just say this. So the rank of pi 1 sigma ng is going to be what? You have 2G. So you have at least one boundary. So the thing deformation retracts to a 1 complex, right? And so how do you figure out how many generators there are of the fundamental group with respect to this, what's the number of loops in this 1 complex, right? So you have 2G from the genus, okay, from this, did I say 2G octagon? I meant not octagon, 2G-gon, I meant 4G-gon before, because you're identifying opposite, right, sides. All right, anyway, but you have 2G plus n and then minus 1, right? Okay, so what does it mean for this to be greater? So what does this mean? What does this mean for this to be greater than or equal to 2? Well, this occurs, of course, if and only if, right, 2G plus n is greater than or equal to 3, right? Okay, so that's what this condition is here, right? So I'm just making it clear what case this is. The line minus n, right? Okay, and then so what is the contribution from Hom? Right, so in this case you have the dimension, right, of the character variety n g g, right. Well, what do you get, right? Well, you have the dimension of g, right, and then you have 2g plus n minus 1. Right, because that's how many, because the Hom space is just that many copies of G, right, because it's a free group. There's no condition for a homomorphism to be satisfied, right, because it's a homomorphism of a free group, right? So then what do you have to do? Well, you have to subtract off, right, the dimension of G for conjugation, okay? But, and that's because it's a free group of ranks, that's because of this, right, condition, because it's at least a free group of rank 2. So your generic orbit is going to be the full dimension of the group modulo the center because the center acts trivially. Okay, and exactly that is why you have to add in the dimension of the center. Okay, because that's, right, to account for, right, you have to subtract, so you subtract, right, that's what it is. Okay, so you subtract off the dimension of PG, G mod its center, okay, which is this, okay? And so what do you get when you do that, right? Well, you get dimension, right, of G, 2G plus n minus 2 plus s, and that is exactly negative Euler characteristic times, right, the dimension of G plus s, and that's, I think, what's there, right? Right, because the negative Euler characteristic, right, is, right, it's, the negative of it makes that positive, and that negative, which is exactly here, right? And then the dimension G, and then the s is the correction term. And that's exactly what we have there, negative Euler characteristic times dimension G plus a correction term, and in this case, the correction term was s. Okay, and the other cases are handled in the same way. Okay, you just have to do these kind of calculations, and I'm not going to bother with it. Okay, here because this is a lemma. Okay, but I will remark that when G is abelian, the reason I excluded that is because it's kind of trivial. The conjugation action is trivial in that case, so the character variety is just a Hom space. But because now G is abelian, this actually is equivalent to the abelianization here. Okay, it factors through that, and it's an equivalence. Okay, and then this is just a free abelian group, and then homomorphisms of a free abelian group into a abelian group are just, correspond by evaluation to just, tuples of the group you're mapping into. Okay, and then you just have to figure out what that power is, and that power, well, there's various cases that you analyze, but anyway. This is just to complete the lemma, just to say I didn't exclude it because it was hard. I excluded it because it was easy. Okay, all right. So now that lemma gives us the means to understand that the algebraic structure of this moduli space does not depend on it doesn't depend on the presentation of the fundamental group. It only depends on the Euler characteristic. Okay. All right. I mean, it generally doesn't depend on the presentation of any. If you define the character variety for any gamma, right, any finitely generated, right, gamma, it doesn't depend on the presentation. But the point here is it doesn't depend on really the surface. It depends on the Euler characteristic. That's what I'm really getting at here. Okay. So multiple surfaces, like say the 3-hole sphere and the 1-hole torus, have the same fundamental group. Okay. All right. So anyway, so here's what the proposition is. So there's a biregular morphism between character varieties arising in this class of character varieties, if and only if you're in the situation where both surfaces are closed, both are open, and their Euler characteristics are the same. Okay? All right, and so what's interesting here is really this direction. So if these are actually isomorphic, then that implies both surfaces actually had to be closed or both had to be open. Okay. The converse does, you can't read that off. In fact, it's necessary to know whether or not you're dealing with either both positive, and the number of boundaries are either both positive or 0. Okay, and let me just say this proposition is not trivial in the following sense, that if you have two characterized that are isomorphic in general, that does not mean the underlying groups are isomorphic. And as a really stupid example, just look at like the cyclic group of order 2 versus the cyclic group of order 3. Right, going into SL23, you can just calculate these things explicitly with matrices, and both moduli spaces here is a set of 2 points, but of course Z mod 2 and Z mod 3 are not isomorphic. Okay, so equivalence in character varieties does not tell you equivalence of the groups. Okay. All right. So so here's just how the proof goes. So first, so I keep doing this with the laser pointer and forgetting, right? Okay, so I'll try to do it this way. So first assume, do this direction first. So first assume that the moduli spaces are isomorphic. That implies, of course, their dimensions are equal. So we need to figure out, can we figure out, something about the surfaces. So suppose that one surface is open and one is closed, right? Well, this relates to the previous talk I gave. If this is if we're in the open surface case, then this moduli space deformation retracts onto this one where K is a maximal compact of G. But these two are not homotopy equivalent when there's no boundary components. And this relates to theorems of myself with Carlos and also Carlos with Indranil Biswas. So basically, knowing that free groups are flawed in the language of the last talk and surface groups are flawless allows us to show that if these are actually isomorphic, then it could not have been the case that one of the surfaces was closed and one was open. Okay? All right. So now that we know that if they're isomorphic, then both surfaces are open or both are closed, right? Now we see from the lemma, right, that the Euler characteristics have to be equal because because if they're isomorphic, the dimensions are equal, and if we know we have either both closed or both open, we can read off their Euler characteristics because the correction terms will be comparable. So we can read off the Euler characteristics from that equivalence of dimensions. So that deduction actually holds without the assumptions on again n1 and n2. Okay, we didn't need to assume anything about n1 and n2. We used the flawlessness of free groups and the flawlessness of closed surface groups to show that we can't have this mixed case. Okay, and so that's the conclusion, right? That either both. So if these are isomorphic, either both surfaces are closed or both are open, and the Euler characteristics of the underlying surfaces have to be equal. Okay. That doesn't imply the surfaces are equivalent, though, right? In the closed case, it does, but in the open case, they just have to be homotopic. Like, again, think one-hole torus versus three-hole sphere. Okay? Later, we'll see we can add additional structure and actually distinguish those two cases from each other. Okay, so now, conversely, assume the Euler characteristics are the same. Then there's three cases to consider. Either they're both they're both open, they're both closed, or it's the mixed case. Okay? So case one, they're both open surfaces and the fundamental groups are free of the same rank because we assume the Euler characteristics are the same. And hence the character varieties are isomorphic. Okay, and I've already said this, the surfaces aren't necessarily homeomorphic, but they will be homotopic. Right? Case two, if the Euler if they're both closed, if they're both closed surfaces, the Euler characteristics being equal implies the surfaces are actually homeomorphic in this class of surfaces, right? And so hence their character varieties are isomorphic too. Okay? All right? That's the deduction we want to get, right? That the character varieties are isomorphic and for the converse direction. Okay. And in case three, we have to ask, well, does this happen at all, right? Is it possible to have a mixed case, right? Where the Euler characteristics are the same, right? And it does, right? So if you have one open and one closed, if the Euler characteristics were the same, you can solve for the non-zero boundary component, and you can actually show that you can arrange for this to happen, right? So it's possible. Okay, so then without loss of generality, just assume the first surface was open and the second one was closed, and then we use the flawedness again here. We know that this is homotopic to this, and this is not homotopic to that, and so therefore every time, so in other words, they couldn't be isomorphic. So that mixed possibility, is impossible. Okay? Now there's a little subtlety here in this direction. I've assumed G is greater than or equal to 2 for this case. Okay? And then so you have to ask yourself, what about when G was 1? I didn't write those details in. If you want to see that, look in the paper. But we handle all cases. Okay? In any event, every time case 3 arises, you have simultaneously that the Euler characteristics are equal, yet the character varieties are not isomorphic. Okay, and so, that completes the argument. Okay, anyway, so, all right, so let's continue on our journey here. That's just a sort of introductory, fact, okay, that is hopefully going to be interesting when we get to the Poisson structure, which says, so we just showed that we can't really, in some cases, distinguish which surface we have from the character variety alone, but we can distinguish quite a lot, right? But now later on we're going to say, hey, we can actually distinguish which surface when we add additional structure. Okay, all right, and here's what that additional structure is. Okay, so when we're dealing with at least one boundary component, we're going to define the boundary map, and that's going to be defined by sending a class of a representation to the class restricted to the boundary component. Okay, and that gives you a class in this moduli space. Okay. All right, and so then now you do that for every boundary component. Now you get a map from the character variety to the n-fold Cartesian product of this moduli space, which we've already discussed what this moduli space looks like. Okay. All right. Now this depends on the surface, not only its fundamental group, right? Because the surface, when n is greater than 0, right, is determined, right? Even if you have the same Euler characteristic, right? Different surfaces with the same Euler characteristic will necessarily have different n's. Okay. All right. Okay, so now we're going to take something in the image of this map. I'm not claiming this map's on 2, but take a point in the image of this map. So it's an n tuple of values of the form that I had on the first slide or the second slide, right? And so you have for each value, for each component of an image point, right? You have the rank of dg components plus the dimension of the central torus, right? That's how many entries there are for each component. So you have n times that number of it's like a vector really, right? It's not exactly a vector in a vector space, but it's a tuple of that many components. Okay. All right, so now look at the inverse image of an image point. Okay, we're going to call call it this. And right, and so we'll see very soon that these are actually the smooth loci of these fibers of this boundary map are actually symplectic manifolds. Okay. All right, so the singular locus is a proper closed subvariety, and I'm going to denote it by the math cal, the script x. So that means I've removed the singular locus. Okay, so this thing right here is I guess a holomorphic manifold. Okay. All right, and then so I said it's a complex manifold that's dense in this moduli space. Okay, and so since this map is dominant, that's something you have to show, but it is. The regular values are generic. And therefore, at such a point, if we intersect this fiber with the smooth locus, we actually get a submanifold of this dimension. Okay, that's the dimension of the character variety that I showed you before, minus again, this is at a regular point of the map. Okay, so then at a regular point, you just subtract off the dimension of the codomain, which is n times r plus s. Okay. All right, so then the union of these leaves foliate the smooth locus by complex symplectic submanifolds. I haven't justified that yet, but that's going to, right? But that's a fact, okay? Making this what's called a complex Poisson manifold, and since everything is going to be in terms of polynomial data, it extends continuously over the entire character variety, even the singular locus. Okay, it's not smooth at the singular points, but it does extend continuously, and that structure makes this what's called a Poisson variety. So this will be an affine variety. In fact, this you can define this for quasi-projective varieties, whose sheaf of regular functions is a sheaf of Poisson algebras. And I'll say what a Poisson algebra is in a few minutes, okay, when I tell you explicitly what the Poisson structure is, okay, for these particular ones. Okay, and indeed, here we are, okay? So in the affine case, which is what we're dealing with, we can make this very concrete. We don't have to talk about sheaves. It suffices to describe the Poisson bracket on the coordinate ring of your affine variety. So what is such a structure? It's a Lie bracket on the coordinate ring of your affine variety that acts as formal derivations. Okay, so in the smooth setting, you actually say it is a derivation in this sense of derivatives, right? But here we're dealing with polynomial functions, so we can actually talk about formal derivatives in the formal Leibniz rule. Okay, and that's all you really need to define the structure on a coordinate ring of an affine variety. Okay, and then you use general theorems to show that on the smooth locus of such an affine variety, even if it's singular, that the more traditional analytic definition of Poisson and symplectic works on the smooth locus. Okay? All right. Okay, so that's what I just said. On the smooth strata V, which will again use the math cal notation, this is a Poisson manifold. Okay, and there's something here to let me point this out at this point. When I say Poisson and symplectic, because I'm dealing with holomorphic functions and I'm in the complex category, a symplectic form is a 2-0 form. Okay, I'm dealing with complex valued data here. Okay, so it's a 2-0 form. We can very often you can restrict scalars to semi-algebraic subspaces of the real locus and get honest 2 forms under some conditions. And in this case, we can do that. And I'll make a remark about that later. But right now, I just want to emphasize everything in this discussion is holomorphic, and symplectic means 2-0 form. Okay. All right, so now with a holomorphic function on the smooth locus of your affine variety, you can define Hamiltonian vector fields in terms of the Poisson bracket, in this sense. Okay, so this is, I'll just leave that alone. And there exists something called a Poisson bivector field, which takes values in the exterior second power of the tangent bundle of the smooth locus. And when you restrict this bivector field to symplectic leaves, you get this formula. The Poisson bracket gives you the symplectic form in terms of Hamiltonians. Okay? And with respect to interior multiplication, the bracket of 2 holomorphic functions, which you should really at this point think of f and g just really as elements of the coordinate ring here. So they're like polynomial functions on your affine variety. But by say like Stone-Weierstrass, polynomial functions are dense, and since everything is on the smooth locus at least analytic, right? This thing will extend to the traditional Poisson bracket on C infinity or a full ring of holomorphic functions if we know the structure on the polynomial functions. Okay. All right. So so the bracket is defined as follows: you take the bivector and then you use interior multiplication on a wedge of the differentials of the functions, and so that just means you precompose. Okay. Okay, and so what does this look like in local coordinates, right? If I take a local chart, right, holomorphic chart, right, in the smooth locus, what do I get? Well, this bivector will look like this in this coordinate system, and these will be, in fact, because we're dealing with the affine varieties, these are actually going to be polynomial functions here. These aij's are going to live in the coordinate ring. Okay. And the bracket then is what does an interior multiplication look like? You precompose here with the differentials. You write down the differentials, and then you do this. Right, when you hit this with this, you get this form here. Okay, and so it's very concrete. So if you know. So what does this imply? This implies if you know the generators of the coordinate ring, you can figure out the complete structure here of the Poisson bracket, okay, by looking at the pairings among generators of your coordinate ring, which you know is finitely generated because, well, I mean, because you're dealing with affine varieties, I guess, right? I mean, general schemes maybe have other questions, but here we're dealing with varieties. Okay. All right, so very good. So, and then last thing I'll note is that the matrices associated to the bivector and the symplectic form, we'll just say the ij matrix here. Okay, there's only going to be a finite number of non-zero coordinates here, or sort of functions here. So you get a square matrix, and here you get a square matrix, right? And so if you look at the relationship here between the bracket and the bivector and the symplectic form on leaves, so on a symplectic leaf, the inverse of the bivector matrix will correspond to the matrix associated to the symplectic form. So you can also compute the symplectic form from the bivector is the point here. Okay, so that's a quick crash course in general symplectic varieties. Or not I shouldn't say Poisson, I should say Poisson varieties here. Okay. Yes, so sometimes symplectic variety means other things for people. Sometimes it means that the symplectic form, there's a desingularization which the symplectic form pulls back to the desingularization. That's not what I mean here. Okay, so I'm just going to use Poisson variety even in the symplectic case to make sure I'm not confusing that notion. Okay, right. So for us, we have a traditional Poisson structure that extends continuously over the singular locus, but we're not saying there's a desingularization that it pulls back to. That's not what we're saying here. That's that latter property is very restrictive, and we're not claiming at all that these varieties have that satisfy that condition. In fact, I don't think they generally do. In the symplectic case, people have worked out, say GLN, and it's only a handful of them that do. Okay, in the closed surface case at least. I don't know if the open surface case has ever been worked out, but anyway, let me just move on. Okay, so I've claimed that these are complex symplectic. So what does the two form look like, right? Okay, so all right, so since G is reductive, complex reductive, it has an ad invariant symmetric non-degenerate bilinear form. I should note that what I'm about to describe works for any Lie group that has this. This is really the condition we need to make what I'm about to write down true. So in particular, if we worked over R instead of C, compact Lie groups would work just as well. Okay, and even more generally, real reductive Lie groups if we wanted to work over R. Okay, all right, but let me just again focus on the holomorphic setting. All right, so extending the case that Goldman worked out in the n equals 0 case, Guru-Prasad, Hubschmann, Jeffrey, and Weinstein showed that even for n greater than 0, you can define a symplectic form on this thing. And I should note that they focused on the real case, but everything they did, so did Goldman, but everything they did extends directly to the complex case. Okay, there's no, it's all homology really and topology of the surface. So it's really just extension of scalars at that level. Okay. But anyway, they are the ones that did the work, and it's true for R or C as long as you have an appropriate G. All right, so here's the picture. Maybe I'll start here at the bottom and work my way up. So one has to do a little bit of work to show that the tangent space of a point in the character variety at a symplectic leaf corresponds almost everywhere to something called first parabolic cohomology. Okay, with twisted coefficients in the Lie algebra. So the Lie algebra is given the module structure by the adjoint action of the representation on it. Okay, so that's, and so what does parabolic cohomology? Well, let me just say it kind of in words. Parabolic cohomology is very similar to regular cohomology. You have cocycles, mod coboundaries. The coboundaries are the same. Okay, what differs is the cocycles. Okay, and the cocycles are going to be regular normal cycles, the usual definition of a cycle in group cohomology, with the group being the fundamental group of the surface, okay? With the condition that if you restrict to the boundary circles, okay, in the fundamental group, so this is copies of Z, right, inside the fundamental group, if you restrict the cycle to those subgroups, they become coboundaries. Okay? Those are the parabolic cycles. Okay? So it lives inside the regular first cocycles. Okay? And it's a sub-object. Okay? All right, subspace. And so we look at the parabolic first parabolic cohomology is the parabolic cycles mod the coboundaries. Okay, all the coboundaries. I mean, you can show that the parabolic coboundaries are the regular boundaries, so it's all the boundaries. Okay, coboundaries. Okay, now here's the thing. Okay, the cocycles generally correspond to tangent vectors of your representation, so that's in the Hom space. Your coboundaries are going to correspond to tangent vectors of your conjugation orbit. Okay, and so generically, you'd expect the tangent space to a point in the character varieties to be the tangent space to the Hom mod that tangent space to the orbit. Okay, that's not always true, but generically it is, and that's sufficient for this picture. Okay, and so what do parabolic cocycles correspond to? Well, you said you wanted the when you restrict to the boundary, the cocycle to the boundary, right? That it is that it is in a coboundary. So that means that in the quotient, the derivative is 0, which means up in the space, the representation is constant on the is constant on at the boundary of the surface. Okay, and those are exactly the points in the symplectic leaves. The points that have that are constant conjugacy class on the boundary circles. Okay, so that's why parabolic cohomology corresponds generically to tangent spaces on a symplectic leaf. So if you want to define a two form, right, that you hope is symplectic, right, you have a function from tangent space cross tangent space to, right, so you want a two form, right, to the complex numbers. So here's how you do it. You go up, over, and down. So what do you do? Well, there's a natural map that sends these guys here, this one into here, and this one into here. Parabolic, this one's natural. This parabolic goes to the regular cocycles where you don't have parabolic anymore, right? This one's a little more subtle. I'm not going to spend a lot of time talking about it, but it's going into the regular cocycles relative to the boundary, okay? And you need that to have cut product, okay? So cut product, when you don't have closed surfaces, you need to have relative cohomology in one factor. And then in which case, when you apply cut product, you get the second cohomology, but now the coefficients now have to be tensored together. Okay, that's the usual thing with cut product. So we have to contract the coefficients down to the complex numbers, and that's exactly where B comes from. You induce the contraction map on this tensor here, and since it's add invariant, it respects the add row module structure on the Lie algebra. Okay, and it allows you to take these coefficients here and get a complex number out of it. In the case of like semi-simple, you can take B essentially to be the killing form. Okay, so if for SLN, you can just literally think of it as the trace. Okay, all right, and so then you end up with something in relative H second cohomology with complex coefficients. So now you take the fundamentals, the orientation class of your surface with boundary, okay, and you use cat product, and that takes you by duality from H2 to lower H0, okay, the zeroth homology, and that's equivalent to just the complex numbers, okay, and that gives you at least it gives you a map, and then of course these guys did a lot of work to show that this is in fact a symplectic form on the smooth locus, okay, all right. All right, so there's the two form. Okay, what about the Poisson bracket? Okay, how are we doing on time, by the way? Okay, so the Poisson bracket, well, again, it starts off by Goldman in the case of no boundary. Okay, and then one of the things I did in my doctoral thesis was to show that his proof, when you switch everything to parabolic cohomology, the proof that he originally gave in the closed case generalizes directly to the open surface case with respect to the Gruber-Sade, Huberschman, Jeffrey, Weinstein two form. You have to have a two form to make sense of this. Okay, so with respect to that form, the formula for Goldman extends to surfaces with boundary. Okay, directly. Okay, but you have to kind of go through every step and make sure it works. And that's one of the things I did in my thesis in that transactions article I showed at the beginning. Okay. So here's how the formula works. So take any two loops up to homotopy, based, is what you want, I guess, for this, up to in here. All right, and then up to homotopy, you can always arrange, and this is something that Goldman showed in his original paper, that you can arrange for alpha and beta to intersect at worst in transverse double points. So what does that mean? That means they're transverse, right, in the usual sense of transverse, right? And double points means the loops intersect themselves only once. They don't like go through the same intersection point multiple times, okay? Now, I mean, this isn't, certainly you can arrange for alpha and beta to not satisfy these conditions, but the point is up to homotopy, you can always arrange it. And for any such representatives, the formula I'm about to show is invariant. So it doesn't depend on which representatives as long as they satisfy these conditions, okay? All right. And so with respect to two such representatives, we're going to let this notation represent the set of those double points. Okay, so just the collection of those intersections. Okay, with respect to a choice, I mean, it's not unique, but you make a choice, and then later on, if you're actually developing this theory, you show the choice doesn't matter. Okay, as long as it satisfies these conditions. Okay, so we've also have an orientation, right, on our surface, whether it's closed or open. Okay, and so you fix an orientation. And then once you fix that orientation, you can now ask about the oriented intersection number of those two alpha and beta at one of the intersection points. Okay? And with respect to that intersection point, you can now look at the fundamental group with respect to that base point and ask how is alpha represented in there at that base point. okay, in terms of the generators of your fundamental group, and we're going to denote that by alpha sub p. Okay? Now, because the space is the space you're taking the fundamental group of is connected, it doesn't matter. They're all going to be equivalent to each other, but the exact form with respect to a generating set of your fundamental group will change. Will change up the cyclic equivalence of the words. So when you look at the product, the expression of the product of two of those curves will, it depends on the base point. Okay? And so that's a very subtle thing in this, but it's there, okay, and you need it. Okay. Now the next ingredient is just take any invariant function in the of G, conjugation invariant function of G, and for every such function you can define a function on the character variety as follows. For any of these alphas or betas, right, you can define f sub alpha as follows. F sub alpha of a character, of an equivalence class in the character variety, is defined by f of rho of alpha. Okay? All right. Right. Okay. So, so now the last ingredient before I can tell you the formula is the follows. You take any such function of this type, f sub alpha. You can use frac b, this ad invariant non-degenerate bilinear form, and you can define a capital F by solving this differential equation. Okay? All right. So, without further ado, here's the formula. The bracket on the character variety in general is of these types of functions which generate the coordinate ring here. Okay? And so consequently, if we know the bracket on those functions by, again, something like Stone-Weierstrass, we get the bracket on, for all appropriate functions by a limiting argument. So the bracket of two such functions evaluated at a representation. So the bracket without the row here, right, is a function, right? It's a derivation on the coordinate ring. So I'm telling you how to understand this when you take this function here and you evaluate it at a row, at a point, right? How does the output occur, right? That defines the function, okay? It's defined as follows. You get the sum over the intersections of the oriented intersection number of alpha and beta are here, okay, times frac b, the bilinear form of the variation. This is called the variation, okay, the variation of little f paired with the variation of little g. Okay, all right. So in special cases, this is actually not too hard to write down. And in fact, Goldman in his original paper wrote down lots of b's and wrote down, because b depends on g, okay? And so, for instance, this whole expression here in the case of SLN, okay, can be written as the trace of alpha p times beta p minus 1 over n, the trace of alpha times the trace of beta. Okay, so in that case, the formula, maybe I'll write it down here. The formula for SLN, if G is SLNC, right, then the formula, then the F, then you can just think of this as the traces generate the coordinate ring. That's the only invariant you need to worry about, okay? And so this is going to be equal to the sum over P in alpha intersect beta. You have to have the intersection number here, okay? And then you have the trace of let me write it this way: alpha P beta P minus 1 over n trace of alpha. You can let go of the P there, it doesn't matter for this one. For here it matters, but here it doesn't, because for any P, these are going to be cyclically equivalent, so the trace won't see the difference. Okay, but here it matters, that the P does change what the product is. Okay, otherwise this thing would just be 0. Or not, maybe not 0, but, oh no, it would just be it would be trivial. So that's very important here. Okay, anyway, so let's go ahead and move on. So I just wanted to give an example there to show that this thing isn't as mysterious as it might look like. Right. So we're going to denote the bivector by A and G. Okay, and I just remark that when alpha represents one of the boundary curves, you can show that it doesn't intersect any other curve, right? Because it's on the boundary, right? And consequently, since there's no intersection, right, that means the sum is 0. It's a sum over the empty set, so it's 0. So in particular, what this says is if alpha is a boundary curve, f sub alpha Poisson commutes with all other functions. And these are called Casimirs. Okay, and it's kind of neat. You can see properties like this just by thinking about the surface without actually doing any calculation, right? I mean, it's a boundary curve, so it doesn't intersect anything, right? It's, you know. All right. Okay, so here's the corollary of this formula, which should be thought of in contrast of the proposition that I proved for you before. Okay, so there's a homeomorphism between your surfaces if and only if the bivectors are equivalent. Okay, and this equivalence here I'm allowing, right, to this to be like scalar multiples and stuff like that. Okay, so that's why I don't have to say this is an orientation preserving homeomorphism. If I wanted these to actually be dead on equal, right, then I'd have to assume that the homeomorphism preserves orientation, because otherwise it would, you know, change the orientation, the intersection number, because it's based on the orientation of the surface. Okay, all right. So yeah, the forward direction is obvious, right? If the surfaces are equivalent, the bivectors are equivalent, because, right, it's the bivectors defined in terms of the surface, right? I mean, like, it's really topological. So, right, that's clear from the formula. Now, you have to, of course, believe the formula, but I'm not here to prove that to you. I'm here to talk about things you can build off of it, right? But of course, I'm summarizing it. Okay, so now the converse has 3 cases. So case 1, both surfaces are open. So then here's what you do. The Casimir subalgebras, those are the things, that's the subalgebra of things that Poisson commute. They differ unless the number of boundaries is the same, because of the observation I made before, right? That the boundaries Poisson commute, right? With everything, right? So thus the Euler characteristics, which are read off the dimension, right? They determine the genus. So the surfaces are equivalent. Okay? I mean, one thing that's kind of implicit in this, right? If we're assuming the Poisson structures are equivalent, I mean, that implies the character varieties are isomorphic as varieties, at least. Okay? So there's like a kind of a pair here, right? The character varieties are equivalent, and we're assuming in addition, right, the bivectors are equivalent. Okay? So that's how I'm able to use that. So here, if the Casimir subalgebras are equivalent, since the character varieties are isomorphic, that means the dimensions are equivalent. If the dimensions are equivalent, we can get the Euler characteristic, and therefore the genuses are the same. So therefore, the surfaces are equivalent. Okay, we have the same number of boundaries and the same genus. Okay, so in this class of surfaces, that's all that you need to distinguish the surface. Okay, so case 2, n equals 0, say, and n1 equals 0, so that's the closed case, and you have an open case, so this is the mixed case. Okay, so now we have the surfaces are not isomorphic. So in that case, this guy actually is symplectic, because there's no Casimirs. Okay. On the other hand, there's at least one boundary here, so that means there is at least one Casimir. So therefore, one's symplectic and one's not symplectic. So that means the bivectors had to be different. Okay, so they're not equivalent. In case 3, they're both closed. Well, here there's the easiest case. We don't even need the Poisson structure. In that case, if we know they're both closed and we know the dimensions are the same, then the Euler characteristics tell us the surfaces are equal. So that's the easiest case. We actually don't even need the Poisson structure in that case to do the converse. Okay, you just need, right, that the character varieties were isomorphic. Okay. Okay, so that's how the proof goes. Right, so if they're both closed and the Euler characteristics are the same, that means the surfaces are, I already said that. The surfaces are isomorphic. Okay, anyway. So here's some examples. I guess I'm out of time, I guess. I don't know, is it okay if I go a little over, or, yeah? Okay, all right. So these are trivial examples. If n and 0 are both 0, or genus is 0 and n is 1, well, then the character varieties are trivial, okay, for any g, so that's not very interesting. Okay? All right, and also 2, 0 is also trivial. The character variety, in that case, the fundamental group is just z, because a twice punctured sphere is a cylinder, right? But there's 2 boundaries. So you're fixing both boundaries to get a symplectic leaf, and so you get a trivial symplectic leaf in that case. It's not interesting either. Okay. The next simplest case is a three-hole sphere. And so here we have the famous, at least to some people, Fricka-Vogt theorem, which says that for SL2 and the three-hole sphere case, or free group of rank 2, the character variety is just affine 3 space, okay, and it's parameterized by the trace of the first curve, the first boundary component, the second boundary component, and the third boundary component. A really quick down and dirty proof is the following, that using the characteristic polynomial, you can show that the coordinate ring of this space is generated by these three functions, but since the dimension is 3 and the variety is irreducible, if there was a relation among those coordinates, then there would be a dimension drop. But since the dimension is 3, there is no dimension drop, hence there can't be a relation. Hence, it's affine 3 space. That's a really, really quick, dirty proof, and you have to believe that the characteristic polynomial can do what I say it does, but it does. Okay, all right, so now, all right, so anyway, so here's what you do with it. Since the boundary curves are disjoint, they have no intersections, and thus the Poisson bracket is trivial. And another way to say it is if you have a three-dimensional variety and you fix 3 coordinates, you've determined a point. So the symplectic leaves are 0-dimensional. So, right, that's, again, kind of boring. But it's boring in a non-trivial way, unlike the first set of examples. Okay, so building off that, let's look at the first non-trivial case, and that is the surface with the same Euler characteristic of the three-hole sphere with the same Lie group of just 2 by 2 matrices. So this is like the simplest non-abelian Lie group, right? And so the coordinate ring is still the same. It's still affine 3 space, okay? Or sorry, it's a polynomial ring in 3 variables. The modular space is still affine 3 space. But now you have a much more complicated situation because you only have one boundary, right? One boundary is for the one-hole torus, right? So now you have 3 coordinates. You're fixing 1 dimension, so you expect a 2-dimensional symplectic leaf, okay? And indeed, if you do the calculation, you get this. I guess I'm out of time. I was going to show you how to do this diagram, I guess, but now since I'm out of time and I have a lot more that I wanted to say, which I'm not. I guess I'm going to end early on my slides. So I'm not going to do the calculation, but suffice it to say, what you do is you draw a picture of the one-hole torus, say a rectangle with a hole punctured out of it, and for each of the pairings, C1 with C2, C1 with C1, C2, and C2 with C1, C2, you draw a picture of those curves in the surface. You look at the intersection, you calculate the intersection number, and then you use this formula here, and you figure out what alpha p, beta p looks like at those intersections. Okay? And in each case, in one case, you get this. This is what happens when you look at, so x corresponds to the trace of the first curve, and this is the trace of the second curve. These are the sort of genus curves, if you will, for the one-hole torus, and this is the boundary. Okay? And so with x wedge y, you get if you do this formula here, okay, you get this. You can kind of see it, right? This is the trace of x. This is the trace of C1. This is the trace of C2. That's x times y. There's the 1/2 there, right? And then you have the trace of C1 times C2, right, which is z, right? And then if you do the intersection number, you get -1, which is why the sign's off, okay, from what's written there. Okay? And then by symmetry, you get similar formulas for the other pairings. Okay? Anyway, so that's where it comes from. All right. So let me hit a little bit of history. Goldman has also, in other papers, computed this Poisson bivector for the Euler characteristic -2 surfaces. So this is the Euler characteristic -1. So there's only 2 such surfaces, the 4-hole sphere and the 2-hole torus. And suffice it to say, those formulas are much, much more complicated. Okay? But no one has gone any further until our paper, and we calculated the first Euler characteristic -3 surface, namely the 5-hole sphere. Okay, now this was sort of an unbelievably complicated computation. In any event, this has like, I don't know, 50 terms. The reason it doesn't look that way is because these sigmas here are symmetry operators acting in the group ring of the mapping class group. Okay, so each one of these sigmas is a sum of mapping class group elements, and it acts on these terms and gives you a sum corresponding to the number of terms you're adding here of of these things. Each of the A sub whatever string of numbers are explicit polynomials in the generators of this, so traces of words. And these symbols here, I'll say what they mean on the next slide. So the T sub brace I corresponds to trace of CI, IJ is trace of CI, CJ, IJK is trace of CI, CJ, CK. A general theorem says for SL2 character varieties, the character varieties generated by such words, so you only need to consider such words if you want a minimum generating set. So as I said, this is the first example of the Poisson structure for a character variety in terms of a order characteristic -1 surface, -3 surface. So here's some of the, this is general remarks. The character variety of the 5-hole sphere in this case has 14 generators and 14 relations. In particular, it's not a complete intersection, okay? And that's a minimal set in terms of this generating set. The dimension of the variety is 9, and the dimension of each symplectic leaf is 4, which that's good, it's even, right? Okay, right? Because you have 5 boundaries, so you have 9 minus 5 is 4, okay? All right, and just to let you put this in context, so our paper is like 43 pages, okay? This computation took 20 of them, okay? And it uses a computational program developed by myself, JP Burrell, and Caleb Ashley in our paper, Rank 1 Character Varieties of Finally Presented Groups, where in that paper, we describe an algorithm to determine the SL2 character variety of any finally generated group at all, not just surface groups, any group, okay? And we implement that in multiple computer languages and make it freely available to anybody who wants to do calculations in SL2 character varieties. And this paper was, in the proceedings of Bill Goldman's birthday conference, and so this was one of the motivations, given Bill's prolific work in this topic and founding the topic really. So a priori, given you have 14 generators, right, you have 196 calculations to do, but using properties of the Poisson bracket, in particular the fact that it's antisymmetric, and you can also look at which, the boundaries are all Poisson trivial, you can reduce it down to 45. Okay, and each of these 45 need to correspond to a topological diagram that you draw by hand. And then for each of these 45 diagrams, you plug them into the computer program, and this gives you at least the explicit structure of the Poisson bracket, but then you have to then do a lot more work to figure out what the symmetry is among those 45 computations. And each one of them tends to be kind of a monster. Like each one of these polynomials here, these A's not all of them, some of them are medium sized, but some of them are outrageously long. So it takes a little bit of effort to figure out the symmetry. And not only what the symmetry is, but also we show that there's actually this is sharp among mapping classes coming from permuting boundaries on the surfaces. There are no further symmetries. So this is like 20 pages, about half the paper is a computer-aided proof of this structure. So this is the point, this is complex computation. Okay, the last part I'm going to do really quick. So you take any two surfaces, you get if you have a continuous map that induces a map between fundamental groups, therefore you get an induced map between Hom spaces, and therefore you get an induced map between character varieties. And then therefore you get an induced map between coordinate rings of character varieties. And so here's the last theorem, and I won't say anything. I'm just going to end here because I'm way over. And the theorem is that if you have a continuous map that between compact orientable surfaces, and I'm not assuming they're connected here. Okay, not assuming they're connected here. Okay, so any compact orientable surfaces that preserves transversality of base loops and double point intersections, then the induced map of coordinate rings is a morphism of Poisson algebras, and if Q preserves orientation, it is a morphism of Poisson algebra if it preserves orientation, and is an anti-Poisson morphism if it reverses orientation, and regardless, the image is a Poisson subalgebra. And the upshot, I'm not gonna give the proof, but let me just say it comes down to understanding the explicit form of the Poisson bracket. And so if you understand that explicit form, you can actually show this quite easily just by seeing what such a mapping would do. Okay, but you have to really know what this formula is. If you don't know the formula and you just know it's Poisson, then it's like, what do I do? Okay, but the corollary is that the induced map on character varieties is Poisson. And that's just almost categorical, since you know, because whenever you have a Poisson morphism of algebras, the induced map on the corresponding spectra is Poisson. Okay, and yeah, I mean, you know, some examples, you can take surfaces that have same Euler characteristic and you can glue boundaries, like a 3-hole sphere. You can define a map from that to the 1-hole torus by gluing 2 of the boundaries. So when like that's an example of a mapping that satisfies the conditions of the theorem. So such mappings are Poisson. And it's interesting because then you have isomorphic character varieties with different Poisson structures and you're relating them. Okay. Another one is the inclusion of a subsurface that satisfies the condition. And in particular, if you're including an open surface into a closed surface, it's contravariant, so the resulting map goes the other way. And that's sort of, I don't want to say it's a symplectic resolution, but you end up with a map from a symplectic case to a Poisson case. Okay, but it's a restriction, not so it's not really. I wouldn't call it a resolution in any kind of sense, but it kind of had somewhat that feeling. And the last remark is that, you know, I mentioned this already, that everything we did works for compact Lie groups just by restriction of scalars. Okay, so we restrict the complex numbers to the real numbers, the 2-0 form then becomes a 2 form, and right, and you have all the theorems hold. Okay. I think I said everything I wanted to say, so thank you. And I'm very sorry for going massively over by 10 minutes. It's crazy. But anyway, thank you all, and thank you everyone in TV land. Sorry for being a little rushed at the end, and I'll stop there.